Hello again. This is a video to review the concept of linearizing graphs. And there's some data here that I've plotted for you on this graph paper. And it's data for the acceleration of an object versus that object's mass, all other things being held constant. And I've done all the things that a proper graph should have. I've scaled the axes, so I'm using most of the paper. I've labeled acceleration with units up here, mass in kilograms. I have a title, data with point protectors, so the data is protected from evil demons or dragons and things like that. And I could make a fit. I can't make a linear fit because the data doesn't really suggest a linear relationship. As we talked about in class, if we're going to study a graph that isn't linear, we need to make it linear, and that process is called linearizing. If I were to try to guess some sort of fit, maybe it looks something, I don't know. It kind of looks like it goes up here, it comes down and curves around, and it looks like it's probably asymptotic to the y and the x-axis. And this is something that you might be familiar with from math class. It looks a lot like an inverse. And in fact, one of the handouts that you have talks about the different shapes that you could see in a physics class and how to linearize that data so that we could study the graph. We have a case where there's a horizontal graph that shows that there's no relationship between the independent and dependent variable. We have linear graphs, and then we have these other shapes that we could get. Of these three shapes down here, the one that our graph looks like is a lot like this. That as x increases, y decreases, such that y is inversely proportional to x. Again, if you look at this shape, it pretty closely matches what I'm seeing over here. So to find out if indeed this relationship over here is an inverse, which we don't really know yet, but it looks like it might be, we could try linearizing the data. And the way that we could try to modify to see if it's this relationship is by graphing y versus 1 over x. So we're going to take every x number, which in this graph, on the x-axis we have mass. So we're going to take every value of mass, and we're going to do 1 divided by that value. So we'll make a new column with 1 divided by 0.3, 1 divided by 0.8, so on and so forth. And I've done that in the next slide over here. The acceleration data is all the same, but I've gone through and changed the masses to 1 over mass. Notice the units are now 1 over kilograms because I've divided mass in kilograms. I've taken 1 and divided it by mass in kilograms. And these are all the new numbers. And this is going to be my new plot. I'll have to resort out my x-axis because I have a new span of numbers. Instead of going from 1 out to 6.5, I have to get out to 3.3 is the biggest number on my new axis. The new axis is not mass, it's 1 over mass. And the unit is not kilograms, it's 1 over kilograms. And so I could label this 1, 2, 3, and 4. I don't have to go beyond that because the biggest number I need to graph on the 1 over mass axis is 3.3. And this axis is still acceleration with units of meters over seconds squared. So this will be acceleration versus 1 over mass. And I could label these, we're going up to 11 again. So I could again do 1, 2, 3, 4, 5, all the way up to 11. Zeros over here. I'll pretend that's a 0. And then I could graph my data points. Right? So one of the data points that I would plot, I have 3.33 on the x-axis, 11 on the y-axis. So go over to about 3.33, go up to 11, and make a data point over there. 1.25 on the x-axis and 4.1 on the y-axis is around here. I'm not being terribly accurate with this. We just go through and make all these data points, And as we make them, we're going to find out that this data ends up looking linear. I've done this accurately in the next slide. So let me go to the next slide. I've worked out all of the data points for acceleration versus 1 over mass. And then I've drawn over this best fit here in green. And the data does look linear. So we've shown that there is a relationship here, that the acceleration is proportional to 1 over the x-axis, which is mass, so it's 1 over mass. Furthermore, I could make a math model out of this. If I find the slope, I can say that since this is a line that should follow the form y equals mx plus b, that I could say that this should be y equals mx, but x isn't just x, it's 1 over x, because I've decided to graph all the x stuff as 1 over x. So let me find a couple of points that I could use. Maybe I could use this point right here, and then maybe I could use... This point looks pretty good. If I use those 2 points, I could find the rise over run for those 2. On the rise, every 3 is 1 acceleration. So 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 2, 3, 2, 3, 1. So it looks about 6.3 meters per second squared on the rise. On the run, it's 1, 2, 3, 4, 5, 6 over. So we have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So we have 2 over here. So the rise over the run that we're going to end up getting is 6.3 over 2. So that's a slope. 6.3 over 2 is going to be approximately 3.15. So let's say 3.2 meters per second squared over 1 over kilograms. That's a pretty weird unit. Since we're dividing by 1 over kilograms, that's the same thing as multiplying by kilograms. So I can say that the slope of this graph is equal to 3.2 kilograms meters over seconds squared. And then I can make my math model. The y-axis represents acceleration. The slope is 3.2 over the x value, well, times 1 over x, times 1 over mass. So this is over the mass value, plus b, the y-intercept, which is 0. So using this form, y equals m times 1 over x plus b, I have this. So this is the equation of this function, which makes sense. It's an inverse, that the acceleration is equal to 3.2 over the mass. And if you plug this in your calculator, if you plug in y equals 3.2 over x into your calculator, you'll get this picture. And the linearization process are the same steps for any of these shapes. But if it looks like it might be a parabola, instead of graphing y versus 1 over x, you'd graph y versus x squared. If it looks like a sideways sleeping parabola, then instead of doing y versus 1 over x or y versus x squared, you would graph y squared versus x. And that's how you could figure out a math model for this particular shape. So that's a brief review of the linearization process.